In this video, I'm going to show one of the models for a nucleus, which is called the liquid drop model. In my previous video, I showed how the general mass of a nucleus can be described in terms of this binding energy, which I deduced a long expression for. And this tells us a little bit about how the forces are holding together the nucleons in the nucleus. Now, the liquid drop model is basically, as it's saying, it's modeling the nucleus as a drop of liquid. And to just justify that a little bit, I'm going to compare liquid properties with nuclear matter properties. So if we have an ordinary liquid, and nuclear matter, we can make some comparisons. For example, that we know a liquid consists of all these molecules. And we know that there's an interaction between the nearest neighbors of these molecules. Now, in an atom, in a nucleus, for example, like this, we found, as I described in my previous video, that between the nucleons, actually, we find that the binding energy is proportional to the atomic mass, so the number of nucleons. And if the range was such that the one nucleon was attracted to all the nucleons, the rest of the nucleons in the nucleus, then actually we expect binding energy to be proportional to A times A plus 1. This is not the case. This is not what we observed. We observed this one, which tells us that actually each nucleon only interacts with its nearest neighbor, so we can draw this analogy. Secondly, liquid has a constant density throughout the material. We can say the same thing approximately for nuclear matter. Also, a liquid cannot be compressed, or it's difficult to compress. And again, we can say the same about nuclear matter. This is difficult to do. We also know over here that we have a homogeneous, so sort of even, mixture. In this case, it's molecules. In nuclear matter, we also have a homogeneous mixture. But in this case, of course, it's of protons and neutrons. Another thing is thinking about the forces. In a liquid, we have van der Waals, which is short range and attractive. In nuclear matter, the equivalent for this is actually the nuclear force. This is also short range. Then we have a sort of hard core force, which essentially ensures that when the molecules are very close together, that they don't sort of get absorbed into each other. And in this case here, it's Coulomb repulsion between the molecules. Over here, we have the same thing for the nuclear force. So in this case, short range, attractive, and then we have at very small distances between the nucleons, you have this hardcore repulsion. So this is how we can draw these analogies. The details of the nuclear force and how this short range and attractive versus the repulsion will be discussed later. Another few points to just notice about the nuclear force, I'm just going to add here at the end because it's just interesting and good to know. Nuclear force, so now we're finished here. Nuclear force. We say that it is charge symmetric and charge independent. And what this is essentially saying is actually that there will be equal interactions between a neutron and a neutron, a proton and a proton, and a neutron and a proton.